in the biochemistry course, we start our discussion on lipids and membranes. Lipids are compounds that have a polar head group and a hydrophobic tail. Now, we are going to understand how these are organized into membranes and what their functions are. So, basically what we have, anything that is non-polar hydrophobic compound soluble in organic solvents is called a lipid. Now, the membrane lipids that we talk about are what are called amphipathic in nature. What do we mean by amphipathic? It means that it has a non-polar end and a polar end to it. Now, the non-polar end arises due to definite chemical moieties, definite groups, and the polar end again arises due to some other groups that are present. Now, if we look at the functions of lipids, they play a very important role in the biological cells and biological cell membranes, and of course membrane transport, which we will be doing later on. We have steroid hormones in digestion as fats and triacylglycerols, which give us the fuel for our bodies, and the membrane structure. So, lipids are involved in all of these activities, starting from hormones to digestion elements that are present in the bile. These are all have lipids as their components. The fats and triacylglycerols are lipids, and in membrane structures, which will what we'll be doing today, we have fatty acids, phospholipids, sphingolipids and cholesterol. Now, initially what we are going to do is we are going to study what the different nomenclature and the different types of fatty acids. Now, what we mean by a fatty acid is a long chain acid. Now, in the organic carboxylic group that we speak about, we speak of a C double bond O, OH being the acid moiety. Now, what we have here is we have a long chain hydrocarbon with a COOH attached to it. Okay? So, these fatty acids are sigma bonded carbon chains. What do we mean by sigma bonds? We have just single bonds here, and what do they have at the end? They have at the end a carboxylic acid moiety, a carboxylic acid functional group. Now, this functional group or this moiety is going to be used in the overall function or overall structure of the lipids that form these membranes. If we consider the fatty acids, the first thing that we are going to look into is their structure and the nomenclature as to how they are identified, and then the physical and the chemical properties of the fatty acids. Then we are going to go into study the triacylglycerols and see how they play an important role in the structure and function and the formation of lipid membranes. Okay. Now, the first thing is about the nomenclature. Now, the nomenclature of fatty acids actually follows two types. One is called the N designation, another is called the delta designation. In the N designation, as you can straight away see, the numbering is from the extreme end away from the carboxylic acid group. So, in this case the number is from here 1, 2, 3, 4 and so on and so forth. For the delta designation, the numbering begins from the carboxylic acid end, and it is this nomenclature or this designation that we will be using, the delta designation. So, if you are to write any particular fatty acid, write the structure of any particular fatty acid, there will be a specific nomenclature that you will follow, and that nomenclature will be the delta designation, where the numbering will begin from the carboxylic acid end, not the N designation. Now, how does this help us? In the next slide, we see the nomenclature as to how we can write this is a fatty acid in the N designation, and what I have below here is a fatty acid in the delta designation. Now, from this nomenclature, you should be able to write the fatty acid. So, we have to know what each of these numbers mean. The first number that you have here is the carbon chain length. So, it tells you how many carbon atoms you have. After the colon, you see another number. So, this 20 means that the carbon chain length is 20. The number after the colon designates the number of double bonds present. So, we have in this case, we have a carbon chain length of 20 and the number of double bonds at 4, and now you can tell me that this is actually the position of the double bonds. Okay? So, the number that we have at the end is the position of the double bonds. The delta 5 means the double bond is between 5 and 6. 8 means it is between 8 and 9, 11 means between 11 and 12, and 14 means between 14 and 15. In the end designation, there is usually just one number put, because usually when we form or when the fatty acids are biosynthesized, what happens is they form in specific units. If you notice here, every double bond is after 3 carbon atoms. It is 5, 8, 11, 14. But so in the end designation, only one is specified, which tells you that there is going to be another one at 9, 12 and 15. And it is opposite to this because obviously the numbering is opposite then in the delta designation. So, the double bonds are assumed to be spaced by 3 carbons. So, here in the end designation only N6 is specified and nothing else. But in the delta designation, the position of the double bonds is written explicitly, where we now know that if this is the nomenclature, it means that you have a carbon chain length of 20, there are 4 double bonds, and the position of the double bonds are 5 and 6, 8 and 9, 11 and 12, 14 and 15. Okay? So, if we look at a set of designations, then we have usually, another thing that we should mention here is that the double bonds that we see in the fatty acids usually have a cis configuration, and most naturally occurring fatty acids have an even number of carbon atoms, because the way that they are biosynthesized is they come in pairs of carbon atoms. Okay, so, if they come in pairs of carbon atoms, all of these are usually even numbers. You do not see an odd numbered fatty acids, because when fatty acid biosynthesis occurs, it comes in pairs of carbon atoms. Now, if we look at just some fatty acids and their common names, 14:0 is myristic acid. So, these are all the delta configurations. So, you should be able to write what myristic acid is. What is it? It is just a long chain, a hydrocarbon chain with 14 carbon atoms. Okay? And you know where the numbering, we do not need a numbering in this case obviously, because there are no double bonds. So, we have myristic acid, palmitic acid, stearic acid. Then we go to oleic acid. It is 18:1 cis. The cis is not usually put in, just the delta 9 is sufficient, because most of them are cis anyway. So, 18:1 delta 9 means that oleic acid is an 18 carbon fatty acid with one double bond at between 9 and 10. Okay, that is as simple as that. So, now you should be, so the one that I had on the previous page was actually arachidonic acid. Okay, it was 20 with 4 double bonds at 5, 8, 11 and 14. Eicosapentaenoic acid, which is an omega 3 fatty acid, has an additional double bond at position 17. So, when we write this, so this is sufficient, this nomenclature is sufficient to tell you how to write a fatty acid. Okay? So, this is basically the nomenclature of fatty acids, and we are going to see how we can use these fatty acids in forming our lipids. Okay. So, what happens if you have this cis double bond? So, here we have a single cis double bond. You see that how the carbon chain has now changed direction, right? If this cis or if this double bond did not exist, it would have been a nice straight chain and there could have been rotations about the single bonds. But when we have it in the cis configuration, then what happens is there is a break in the chain because of the cis configuration. So, you have what is called a kink in the chain. Okay? So, instead of having a normal long chain that you would have had and free rotation about the single bonds, each cis double bond causes a kink in a chain. So, if I had another cis double bond at this position, this part of the fatty acid, part of the chain would fold back. So, I would have a kink in the structure. So, I have a kink in the structure due to the fact that I have double bonds in the hydrocarbon chain. Okay. So, what do we have? When we have these membrane lipids now, this is something we are going to study in detail later on. These are my fatty acid chains. So, what is going to happen is I am going to have a polar head group. We will see what those polar head groups can be, and my hydrophobic tail, if it is a straight chain fatty acid, will look like this. If it happens to have one fatty acid that has a kink to it, it is going to be shaped like this. Okay, we will see how I am talking about two fatty acids linked to a single polar head group in a moment. But when we are talking about the polar head group and different fatty acids, when they link together, you see how you can change the structure of the lipid because of the type of fatty acid that is being attached to the polar head group. Okay? So, you are basically changing the structure depending on the choice or the type of the fatty acid that you are considering. So, basically if we look at that fatty acids, this would be the structure where we would have a carboxylic group here. So, this would be the polar part of it, and if we have a long chain, it would be a smooth long chain, a straight chain. If you happen to have a cis bond here, what would happen? The chain would get bent. Okay? So, you would have what is called a kink, and you recognize that if you had another cis bond here, what would happen more? It would twist even more. Okay. Now, some properties of fatty acids. Here are some physical and chemical properties. Fatty acids are weakly acidic in nature, weakly acidic with a pKa of 4.5 to 5, which means that they are ionized at physiological pH, because physiological pH is 7.4. Saturated fatty acids are solid at room temperature. The melting point, you understand, is going to depend on the chain length and definitely the number of double bonds present. Okay, on the degree of unsaturation. We will see how that is going to play an important part in our lipid formation, membrane lipids. So, we have weakly acidic fatty acids. The saturated fatty acids are solid at room temperature. The melting point depends upon the chain length and the degree of unsaturation. The cis bonds, you understand, with the kink in the cis bonds, what happens is it disrupts the molecular packing. Okay? So, it lowers the melting point. Okay? Because if you had straight chains that were normally completely very well organized, you would have a higher melting point. But due to the presence of the cis double bonds, the intermolecular packing of the hydrophobic chains is disrupted, it is broken, and that lowers the melting point. The polyunsaturated fatty acids that you see in a lot of vegetable oils that you consume, that say that they are PUFA, that is what it is called, polyunsaturated fatty acids, they are readily oxidized by exposure to air, and these fatty acids can form micelles. Okay, we will see, why they can form micelles, because they have a hydrocarbon chain and it has a polar head group to it. Okay. So, these are the basic physical and chemical properties of fatty acids. What we have to remember is that they are weakly acid. Saturated fatty acids are usually solid at room temperature, and the melting point is going to depend upon the number of carbon atoms you have and on the degree of unsaturation, and the more the number of cis bonds that you have, the lower the melting point is going to be, because you are going to disrupt the intermolecular packing between the hydrophobic chains. Okay. Now, we are going to come to what are called glycerophospholipids. What does this mean? We have glycerol. Glycerol is CH2OH, CHOH, CH2OH. Okay. Now, glycerophospholipids are what comprise lipid membranes. Okay. They form, or they are the constituents of cellular membranes. Now, you recognize that these OH groups that you have here can be esterified by acids. What is an esterification reaction? We have an ROH and a RC double bond OH. With the removal of water, we form an OCO, an ester formation. That means that these H's, if they react with fatty acids, can do what? They can be esterified, and I can have to this glycerol a long chain attached to either this hydrogen or this hydrogen or this hydrogen. Usually, there are two fatty acids attached to it, which is why I had two lines sticking out from the polar head group. So, what do we have? We have the hydroxyls at C1 and C2 that are esterified with the fatty acids. So, what happens? So, we have our glycerol. It is, in this case, the one that I show you here is triacyl glycerol, which is what comprises the fat droplets that we have in cells. If you see, there are triacyl or triglyceride tests that have to be performed in blood to see whether you have an appropriate triglyceride content. If you have more fat droplets, then you have a fat restricted diet. Okay? So, this is what a triacyl glycerol would look like. What do we have here? Here is the structure of glycerol. We have 3 OH groups here. If each of them, number 1, number 2 and number 3 are each esterified, this is what it is going to look like. So, in the first carbon atom and in the third carbon atom, we have straight chain fatty acids that have been used to esterify the OH groups of the glycerol. The extreme OH groups of the glycerol have been esterified with straight chain fatty acids here. In the middle, we straight away know that this has now not only one, but it has 2 cis double bonds, which is why it is even bent further than the one I showed you previously. Okay? If you look at the structure here, this is linoleic acid that has been used. We have one cis bond here and another cis bond here. So, it has changed the structure of the hydrocarbon chain into making it more disrupted, it is more kinked in a sense. Now, we are going to see how we can change the properties of the groups here and then change what lipids or what the glycerophospholipids are actually made of. Okay. What we have therefore are called phospholipids. What are these phospholipids? In the 2 classes of phospholipids that are present, these form cell membranes. We have glycerol phospholipids that have what is called a glycerol backbone, just like I showed you. We have sphingomyelin that forms from a sphingosine backbone, and in this case, this actually forms a lot of the membrane. Each of these will form a lot of the membrane, and these phospholipids are usually referred to as PL. Now, what is essential of these? They are extremely important for membrane structure. They are found in membrane lipids, okay? And we will see how what these structures actually are. So, what we need to know is there are 2 types of phospholipids. and they are essential for the membrane structure and they are found in membrane lipids. Okay. This is the breakup. What we have here is we have storage lipids. Storage lipids like storage in terms of fat droplets. Okay. What are the fat droplets? They are triacyl glycerols. Okay. So, what we need to know is the storage lipids which are neutral in nature have 3 fatty acids attached to the glycerol. Okay. We have membrane lipids. In the membrane lipids, we have phospholipids and glycolipids. In phospholipids, we can have glycerophospholipids or sphingolipids. Okay. It is just a breakup tree. So, the membrane lipids are polar in nature. They have because they have a phosphate group attached, we will see what that means in a minute. Phospholipids are glycerolipids, glycerophospholipids or sphingolipids, and glycolipids are other sphingolipids. Glyco means you have sugar. Whenever the word glyco comes in, a prefix glyco means there is sugar present. So, if we go back to the phospholipid breakup, we have storage lipids that are triacyl glycerols, fatty acids. We have membrane lipids that are phospholipids or glycolipids. The breakup of phospholipids is glycerol phospholipids or sphingolipids, where the backbone is basically different. Okay. Now, we will study this in a bit more detail. This, you recognize the black part here is part of glycerol, CH2OH, CHOH, CH2OH. Okay. Now, what has happened at the first 2 carbons is the C1 and the C2 have been esterified by fatty acids. So, we have long chain fatty acids in both cases. The third carbon has been esterified with a phosphate. Remember, that is also an acid. So, we have 2 of the carbons esterified with fatty acid chains and 1 with a phosphate. This is called a phosphatidate. Okay. So, what is the basic structure? The basic structure is glycerol. The 2 carbons of glycerol have been what? Esterified to with 2 fatty acids and the third with phosphate. So, we have a phosphatidate or rather a glycerophospholipid. So, this is what it looks like. What do we have? We have a fatty acid on the first carbon, we have a fatty acid on the second carbon and we have a phosphate on the third carbon. Now, the phosphate again is esterified. Okay? If the phosphate again is esterified by this X group, okay, this is where we can change the type of glycerophospholipid that we have. So, where can we make the changes? We have the basic structure of a glycerophospholipid, that is going to be the glycerol. We have one fatty acid linked on the first carbon, a second carbon linking another fatty acid. So, obviously, we can change the type of fatty acid that we have. As soon as I change the type of fatty acid, the type of lipid is going to change. Then, I have an esterification on the third carbon atom with phosphate and I have a polar head group here, which we will see how that affects it. So, what do I have? Where is my polar head group? It is here. Here are all the oxygens and the phosphates and so on and so forth. And where are my chains? R1 and R2. So, what do I have? I have the basic structure of the lipid that is going to look like a polar head that is this part here, and the R1 and the R2 are these chains. Okay, you understand what the structure looks like now? We have the overall glycerol. 2 of the OHs have been esterified with long chain fatty acids, which is why I have 2 legs to this polar head group. And the polar head group forms because of the phosphate esterification and an additional polar head group. Okay? So, this is the basic structure of a glycerophospholipid. Now, what can I change here? I can change type R1, I can change R2, I can change X. In that, I will be changing the complete type of glycerophospholipid that I have, and we are going to see how we can do that. Okay, so this is our structure. So, we have the PiOH. What is happening to this OH? It has been esterified again. It can be esterified with serine, choline, ethanolamine, glycerol or inositol. Okay, there are different groups that can be used to esterify the phosphate in the phosphoglyceride. And the 2 fatty acids that we have, R1 and R2, are usually not the same. We will see why later. So, how can they be different? They can be different in their length, they can be different in the number of double bonds, they can be different in the location obviously of the double bonds. So, that is where we have our differences R1, R2, X. So, what are these differences? Okay. This is phosphatidyl inositol. So, you recognize now the glycerol moiety. Let me show it to you here clearer. Okay. So, here is our glycerol moiety. So, this is one carbon atom, this is the other carbon atom, and this is the third carbon atom, right. So, what was our glycerol structure? COH, then we had CH, OH, and again we had CH2OH. This has been esterified, this has been esterified. So, we have long chains here, and in this case we have it esterified with the phosphate. Linked to the phosphate again now is another group. This is the X that I showed you in the previous slide. So, it is this group X that in this case is inositol. Okay. So, what do I have? I have, now you recognize when you have all this number of OH here and the phosphate here and the negative charge here, what does this comprise? It comprises the polar head group. So, it is this part that forms the polar head group, right. And what is R1 and R2 forming? The tail. It can be different depending on the type of R1 and the type R2. Okay? So, this is the basic structure of a glycerophospholipid. Now, what can we change? We can change inositol to make it something else. So, let us see what we can change it to. Okay. We can make it choline. Again, the basic structure is exactly the same. I have R1, R2, I have the phosphate. Linked to the phosphate, I have another X. What is that X? Choline. So, I have, instead of phosphatidyl inositol, I have phosphatidyl choline. I can also have phosphatidyl ethanolamine. I can have phosphatidyl serine. Each of these, the difference you understand is going to be just in the X group in this case. So, we can have identical R1s and R2s for phosphatidylcholine, phosphatidylserine, phosphatidylethanolamine and so on and so forth. Okay? So, these are the different types of glycerophospholipids that we can have. What you need to remember is the basic structure is a glycerol. You have two fatty acids R1, R2, you have a phosphate and the phosphate is linked again to another polar head group that is going to result in a polar head group to your lipid. A sphingolipid. What is a sphingolipid now? Now, the sphingolipid, this is the structure. It is based on the structure called sphingosine. Okay. Now, this is the structure of sphingosine. What you see here is you have a CH2OH. You have in the middle CHNH3 plus, and in the last carbon you have a CHOH to which is linked a long hydrocarbon tail. So, this is the basic structure of sphingosine. Now, what can happen here is, what groups do we have here now? We have a long carbon chain as it is. Okay. So, by default sphingosine comes with a long hydrocarbon chain. It has a polar region here that constitutes an amino group. It has an NH3 plus. Now, what can happen with the NH3 plus and a fatty acid? It can form an amide, right. So, what can happen here is, you see in the part here that we have an R C double bond O N H, because we have just like an amino acid linked to an NH3 plus would give you what? An amide. You can have an amide formed here. So, the amino group of the sphingosine that can form an amide bond with the fatty acid gives you what is called a ceramide. Okay. Have you heard the word ceramide before? They sell you shampoos with ceramide in it. If you look at the advertisements of shampoos, they will tell you that ceramides are present in it. Okay. This is what is a ceramide. So, what do you have in a ceramide? You basically have a sphingosine. What is a sphingosine? It is these sphingolipids are going to be derivatives of this. It has nothing but to it, it has a long hydrocarbon chain. There is an NH3 plus attached to it and an OH attached to it. Now, this already has the long hydrocarbon chain attached to it. So, what you can have is, you can have this NH3 plus form an amide with another fatty acid. So, what are you going to have? You are going to have two long carbon chains here. Okay. So, that is exactly what you have. So, we have ceramides that are usually include a polar head group and they are esterified to the terminal OH of the sphingosine. Let's see what that is. Okay. So, what did we have? You recognize the basic structure of the sphingosine now? This is the basic structure of the sphingosine, the one in black. This is the long carbon chain that you had. This is the long carbon chain. Okay. So, this is the sphingosine moiety. This is the fatty acid attached to it to form an amide. And what do we have here? We have, remember there was an OH here. So, this can attach to another group forming a sphingomyelin. So, we have what is called a sphingomyelin, which is a ceramide with a phosphocholine. What is a ceramide? A ceramide is when you have OH here and the amide here and the sphingosine as it is. So, in the basic structure of the sphingosine, if you have the fatty acid linked to form an amide, it is called a ceramide. In this case, when you have phosphocholine to form a head group here, this forms what is called a sphingomyelin.
So, this is after the formation of a ceramide. So, you have an OH group, initially this was an OH, it is now linked to phosphocholine to form what is called a sphingomyelin. Okay? So, that is basically it. Okay. Now, again there is one other thing that we need to know. Again we remember what a sphingomyelin or what a ceramide is. What is a ceramide? A sphingosine with a fatty acid with OH. Now, you have to recognize that that H can be replaced. If you replace this H with phosphocholine, you have sphingomyelin. If you replace it with a sugar, you have what is called a cerebroside. It's just nomenclature. All you need to know is you have a glycerol. Let's consider here. You have a glycerol, you have sphingosine. These are the two backbones. That's it. Okay? What you have is you have 3 OH groups here, right? If 3 of them are fatty acids, you have a triglyceride. If 2 of them are fatty acids, 1 a phosphate, you have a glycerophospholipid. If that phosphate again is attached with another X, you have a series of lipids. In sphingosine, you have a different type of, you have basically a shape like that, because you have a long carbon chain in the structure of sphingosine itself. What you have here is you have a fatty acid attached in forming a ceramide. Then this OH can be linked to what? Can be linked to a sugar to form a cerebroside. It can be linked to a phosphocholine forming a sphingomyelin. Okay, so that is the basic structure of all this. So, we can have a cerebroside if you have just a simple sugar, or you can have a ganglioside when you have a complex oligosaccharide attached to it. Okay, it's just nomenclature. They are usually found in the membrane bilayer, which is why we have to consider all the different types of possibilities of the sphingolipids or the lipids themselves. Okay. Now, what can we do with this? If we look at the molecular arrangements of the lipids, you know that they can associate with water, okay, because the cytosol or the cell itself is embedded in water, embedded in the blood, embedded in the cytosol. So, what is going to happen is the hydrophobic tails will never be in the cytosol. Okay? So, we have to have what is called a bilayer. So, it is this polar part that is going to be, say, outside the cell, this polar part that is going to be inside the cell. So, we have a bilayer that has polar head groups in either directions. So, the amphipathic lipids in association with water will form complexes in which the polar regions are in contact with water and the hydrophobic regions are away from the water. Okay? So, it is a very smart way of forming the lipids where you have a strong bilayer which is not going to allow everything in and out of the cell, but at the same time it is going to be extremely important in the characterization of the lipid bilayer. Now, there is another way we can organize this. How is that? In a spherical manner. Okay? Now, what do we form in the spherical manner? We form what are called spherical micelles. Now, what are these micelles? These micelles have polar head groups outside and we have the hydrophobic tails inside. Now, we can also have what is called a reverse micelle. What is a reverse micelle? Where you have the opposite of this. If you put this in an organic solvent, what is going to happen? If you put this spherical micelle with the polar head groups in an organic solvent, it is going to reverse and the polar head groups are now going to be in the center and the hydrophobic tails are going to be facing the hydrophobic or the organic solvent. So, we have what we call the reverse micelles or the normal micelles. Okay. Now, if we just go back to this once more, when we have a cerebrocyte or a gangliocyte, some structure like this form a micelle, then we have a long fatty acid chain at the R group. We have another long hydrocarbon chain in the sphingosine moiety at the because of the sphingosine structure itself. So, when this forms a micelle, we expect this part to be the polar head group on the surface and these two to be the legs of the structure. So, the structure that we have here is basically going to be the bilayer with the two long chains. In case of a glycerophospholipid, both of these are fatty acid chains. Okay? But in case of a sphingolipid, one part is the hydrocarbon chain that belongs to the sphingosine and this is the ceramide, the amide part that has been linked with the OH by the, not linked to the OH, it is linked to the amide of the sphingosine to form an amide. So, we have one fatty acid and one sphingosine hydrocarbon chain here, and so the same thing that we would have here. So, what are these structures that you can have? This is a micelle. Now, micelle is obviously not 2-dimensional, it is 3-dimensional. Okay? So, it actually looks like this. So, this is just like half of it cut off, as you can see. So, we have different types of micelle structures. What are these micelle structures? So, all of these red balls that we see here, red spheres along the surface are all polar head groups, and all the chains that are inside are all the hydrophobic chains that we see. Now, when we consider what a liposome is, okay, because we have to consider the way the transport of material occurs in the body. Okay. If you have a micelle and you have a polar ingredient or a polar substance that has to be transported, you understand that it is not going to be possible for this particular micelle to transport it. Why? Because it has a hydrophobic core, right, a hydrophobic core to it, and it would be possible to transfer a hydrophobic component, but if it happened to be a polar part, it would be difficult to do so. So, we have the formation of liposomes. What happens here is, you see, there is a lipid bilayer sort of a thing that forms a membrane, and inside we have a polar center. Okay? Now, the reason why I am telling you this is used for a lot of drug delivery. Okay? When you have drug delivery or when you are creating or making drugs, you have to ensure that at times that your drug is water soluble. Okay? Because if you want it to interact with blood plasma, okay, you have to have one that is going to be easily solubilized, which is a lot of the problems with drugs, is they are not easily solubilized. Now, the transport of a lot of material takes place through these liposomes. Now, you understand that in the center here, what can happen? We can have any polar moiety, any favorable ionic interaction that might occur will hold the drug in this position, and it will transfer it to basically where it has to go. It will circulate in the blood and then be able to transfer itself. In the case of a bilayer, what we have is we have the most stable configuration for amphipathic liquids. Okay? So, this is a possible structure and it is usually used in transport, but the most favored you see, but this is sort of a confined structure. If we have a lipid bilayer, then we have the polar groups forming a sheet on one end, the polar groups forming a sheet on the other end, and we have a lipid bilayer. And it is this bilayer that is going to result in all of the transportation, all of the lipid structures, all of the membrane structures that we will be seeing in the next class. So, basically what we have learned is that we have our glycerol. In the glycerol we have storage lipids. What are storage lipids? Storage lipids are those that are fat droplets. Okay, what are these fat droplets? The fat droplets are triacyl glycerols, triacyl glycerols or triglycerides. What is the basic structure in this case? We have our 3 carbon glycerol, we have our OH, we have our OH, we have our OH, right. We have this replaced by a fatty acid, this replaced by a fatty acid, this esterified to fatty acid. So, each of these esterified to fatty acid is going to give our triacyl glycerol. What can they be esterified? They can be esterified by a series of fatty acids, and we learnt that if we have such a nomenclature, delta 5, 8, 11, 14, we know how we can write this. Okay? We have normally a long carbon chain where we have the COOH attached in a normal fatty acid. Okay? When we have a nomenclature in the delta designation, we have 18:4. The 18 stands for the number of carbon atoms, the 4 stands for the number of double bonds, and these are the positions of the double bonds from 5 to 6, 8 to 9, 11 to 12 and 14 to 15. Okay? So, once we have these fatty acids, we can have a cis configuration to the double bond. As soon as we have this in a cis configuration, this changes the direction. Okay? As soon as this changes the direction, then what happens is I have a what is called a kink. So, this gives rise to the kink in the structure, and I am going to have, therefore, in my glycerophospholipid, what do I have? I have my H2, I have an R2 here, I have an R1 here, I have, what do I have here? I have my phosphate and I have to this linked an X. So, this is my polar part. So, what can happen is if this forms R2 and for R1 I have a straight chain carbon fatty acid and this is my polar head group, I will have a polar head group, that is this part. I will have a long carbon chain which is this part if I happen to have no double bond formation, and if I happen to have a double bond formation, I will bend it like this. Okay? Then what is going to change? What are the properties then of the fatty acids? I have specific properties of the fatty acids that tell me that the pKa's are around 4.5 to 5, making them or ionizing them at physiological pH, and I have specific melting points for these depending on what? Depending on the length of the chain, and on the number of double bonds that we have there. Because the more the number of double bonds, what are you doing? You are disrupting the organized structure that it would have. What would happen if it would have? It would look perfectly. So this is the way they would be organized. But if you had a kink, you would have, say, one that was shaped like that, one that was disrupted like that. So what would happen to this? This would melt easier than this. So the more the number of double bonds, the disruption in the structure, and you would have lower melting point, which is why a saturated fatty acid is solid at room temperature. Okay? And then we went on to study all the different types of lipids and what we could have, and these are the different types of molecular arrangements of lipids that we can have. And then in the next class we will see how we can organize this into an actual lipid bilayer in the protein, and we will see how proteins are embedded and how they can help in the transfer of material inside and outside the cell. Thank you.